We had been talking about the Bohr model of the atom, which is a lot like the solar system. And now we're going to talk about the quantum mechanical model. So this replaced the Bohr model in the early 20th century, so the early 1900s. And this was revolutionary because scientists determined that electrons do not behave like particles flying through space. If you're at all familiar with Einstein and his theory of relativity, you realize that when you take things to extremes, funny stuff happens. And so, we're familiar with baseballs and how if you throw a baseball, it travels. And if you take a smaller object like a marble and you throw it, it still behaves in the same way. But if you go down smaller and smaller and get down to an electron, if you throw an electron, it does not behave in the same way as a baseball. It's a little hard to wrap our brains around, but we're going to give it a shot. So in the Bohr model, we had orbits, which are like the orbits of the planets around the sun. In the quantum mechanical model, we have things called orbitals. Okay, so there's an AL at the end of the word orbit, and that's important. These are different, okay? The orbitals are probability maps. Okay, so, oops. This is messed up. Okay. Probability maps. They're not paths that the electrons follow. They're probability maps that show statistically where an electron is likely to be found. We can't say the electron is here at this time or it's there. They're very squirrely, unpredictable little things, those electrons. So let's compare baseballs and electrons. And this is appropriate because Saturday was opening day for Little League. So you can find me at the Little League park most nights of the week now. So a baseball's path can easily be traced. Okay, so the pitcher throws the ball and the catcher catches the ball. Now he can do funky things in how he throws the ball. He can make it curve or drop or do different things, but it's predictable, right? And if you've taken physics at all, they can describe the path of the ball and the effects of gravity on it and all kinds of stuff. So a good pitcher can throw that baseball and it'll go to the the catcher's glove every single time, right? It's predictable. Electrons do not behave that way. If you were able to throw an electron in the same way that you can throw a baseball, if you threw the electron in exactly the same way, it would not go to the same place every time. It would go to a different place every time. So, imagine a pitching machine. You set up a pitching machine, you load it up with balls, and it shoots the ball in exactly the same path every time. If you do that with electrons, they don't go in the same path. So imagine the electrons being pitched at this batter here. Each of these little spots here is where the electron would end up. So throwing the electrons in the same way where if it was a baseball, you would expect it to end up right in the center of this circle here, they would go in these different places. And so what you get instead of a point or a specific path is you get a probability map. If you throw the electron enough times, you'll get an idea, well, most of the time it ends up in here. So 20% of the time it ends up in this smallest circle. 40% of the time it's within this larger. 70% it's within this larger circle. And if you made a larger circle, you could say, well, 90% of the time that we throw the electron, it's going to end up in that area. But occasionally, it might actually go in the opposite direction. Okay, it's hard to understand because anything that's large enough that we can see and manipulate cannot act like this. But electrons, like photons, act as waves and as particles. And so we call this wave-particle duality. So an orbit is a circular path showing the electron's motion around the nucleus. And that's why the Bohr model just makes more sense to us, because we can visualize it. An orbit is predictable. An orbital, in the quantum mechanical model, is a probability map. And it just shows relative likelihood of an electron being in a certain volume, in a certain space. And it's completely unpredictable exactly where that electron is. So we specify the different orbitals with letters and numbers. So the first specification is a number, and that's called the principal quantum number. And it specifies the principal shell of the orbital. When we talked about the Bohr model, we talked about orbit 1 and orbit 2 and orbit 3, and how as the numbers went up, the energy of the electron was greater. And we talked about how if you zap an atom with electricity, you can cause the electrons to go up to higher energy orbits, and then they'll come back down. So these principal shells are a little bit like those orbits. They're different levels of energy. And so if you go to a higher number, you have more energy. And then there's a letter that indicates a subshell, and it specifies the shape of the orbital. And the orbitals have different shapes. And the possible letters are S, P, D, and F. And I know some of you are wondering, why not A, B, C, and D? That would make more sense. These actually have some historical meaning. I always forget what S is. I really should look that up. P was principal, D was diffuse, and F was fine. And it had to do with the characteristics of the line in the emission spectrum of hydrogen. So there is meaning behind that, which doesn't help you guys out at all. So let's look at the lowest energy orbital. So it has the lowest number, number 1, and an S designation. The S, well, first of all, it's important to recognize that orbitals are three-dimensional. They're not flat, they're three-dimensional. And so here we've got a representation of a 1s orbital. And we see we've got a graph in 3 dimensions here. And here we're imagining that we're taking a photograph of the electron in this atom, say every second for 10 minutes. And one time it's here, and another time it's here, and another time it's here. And as you take those pictures and superimpose them, you see that most of the time the electron is in this area. And so this area out here is where the electron probably is. And so this has a spherical shape. And the dot density is going to represent our probability of finding an electron there. Any questions? So I think of electrons as a little bit like my son Andrew. He's 5, and he's very random sometimes. And you just never know where he's going to be, right? So let me just draw a picture for you. Okay, so, ooh, that's not a good color on white. Let's go with red. So this, roughly, very roughly, is an outline of my house. Okay, and here's the yard. And so let's think about, where is Andrew? Andrew's family color is orange. And so if at any given time you asked, where's Andrew? Well, Andrew's right there. And then 5 minutes later you say, where's Andrew? Andrew's over there. Where's Andrew? He's here. Where's Andrew? You kind of get the idea? He's all over the place. When he was 2, he stole the neighbor's big wheel and drove it 3 blocks to his uncle's house. Who does that? Scared us. okay? We did find him. He always comes back. Darn it. But those pictures of where the electron is are a little bit like this picture I've drawn. So we don't know what the electron did between the two spots, you know, and we don't know where it's going to be next time. But by taking those pictures, essentially, we can predict where the electron's going to be. So if Andrew is at home, there's, you know, probably a 95% chance that he's actually on the property, right? There's a 5% chance that he's not, that he, you know, took off. He's getting better about that. This over here is the living room, and on the weekends when he's allowed to watch television, then you can find him more there, right? You know, and then sometimes he uses the bathroom, and there's a bathroom over there. This right here is his bedroom, and he's not usually in there, not even at night, because he doesn't like to sleep in there, just because. So let's go back to our electrons. So in this picture, we're representing the electrons as dots, and so this is a probability map. We can also represent them, that orbital, as a geometric shape. So here we see an illustration of a sphere, a ball shape, and the s orbitals are spherical. And so when we draw a sphere like this represents the volume within which the electron is found 90% of the time. So 90% of the time, the electron will be somewhere inside that sphere. 10% of the time, the electron will be outside of the sphere. It doesn't have to be in there, okay? And so here we have the superposition of the sphere and the dots. And we see that there's dots on the outside of that sphere. The electron could also be like right up here too. So a hydrogen atom has one electron. That one electron is going to be in the lowest energy level, and that's called the ground state, or the lowest energy state. Because electrons are going to seek out the lowest energy orbital available. Nature tends to go towards things that are lower energy. A boulder sitting on top of a mountain has more potential energy than a boulder at the bottom of the valley. And so that boulder will tend to roll down the hill, right? Have you ever seen a boulder roll up a hill? No, it doesn't happen too much. So everything's going towards lower energy. But if we zap that atom and put a bunch of energy into it, that electron can go to a higher energy orbital. That's an excited state, and it's unstable. Okay, and we saw that in our pictures with the Bohr model. We saw it jumping up to a higher orbit and then coming back down. So when the orbitals, in the quantum mechanical model, we still have that concept of going to higher energy levels and coming back down. So all atoms are going to have one ground state, one lowest state of energy. And they have many different excited states because they can be excited by different amounts of energy. So this is the 1s orbital. That's the lowest energy orbital. The next highest energy orbital is a 2s orbital. And when we draw these axes, they are centered on the nucleus. So the nucleus of the atom is at the center here, and this sphere is centered around the nucleus. So the 2s orbital is also a sphere, it's just larger. Okay, and so when we draw this sphere, 90% of the time an electron that's in that 2s orbital will be inside of that sphere. So the 2s orbital is just slightly larger than the 1s orbital. The next type of orbital is the 2p subshell. So this is roughly the same energy as the 2s, but it's a different shape. And there's actually 3 different orbitals within this subshell. And they're shaped kind of like dumbbells or like 2 balloons. Okay, so here's the probability map. And we see here there's darkness here. And this would represent where the electron would be found 90% of the time. And there's a gap here in the middle. It's not found in the nucleus. So 90% of the time an electron in this orbital would be on one of these sides. And this represents an orbital with 1 electron in it. It could be on either side. And another orbital is at right angles to that. And this one is vertical at right angles to both of those. So they're just oriented differently in space. They don't overlap, these p orbitals. I'm just going to tell you, I understand that this is hard to understand. It's hard to explain, too, because it's just so crazy and out there. So n equals 1, that's the lowest shell, the lowest energy level. And in that level, there's only one subshell. That's that spherical S subshell. When we go up to the second energy level, there are 2 subshells, the S and the P, which we just looked at. If you go up to the third level, now there are 3 subshells. You see a pattern here with these numbers? 3 subshells, and there's an S and a P, and then there's another sort of subshell called a D, and it's even weirder than the P. And if we go up to the 4th level, we have 4 different subshells, and that's where we get the S, P, D, and F. Okay, so here's my crazy analogy, which my husband thinks is just really stupid, and maybe it is, but some students like it, so I'm going to tell it to you. Have you ever been to Las Vegas? They have some really weird architecture in Las Vegas, right? There's that casino that looks like a pyramid, and it's like all gold and shiny. Okay, so imagine that this is a Las Vegas casino. This is an inverted pyramid kind of thing. Now, would that make a good building? No, it wouldn't. But this is pretend, so it doesn't have to make a good building. So imagine this as being like a hotel. And these are the different floors in the hotel. So on the first floor, the second floor, the third floor, and the 4th floor. And of course, the rooms cost different amounts of money to stay in. The rooms on the ground floor are the cheapest, and as you get higher up in the hotel, because the view is better, you have to pay more. Okay, so people are coming in to stay in this hotel. And these are not rich people. Actually, not a lot of rich people go to Las Vegas. People go there thinking that they're going to get rich, and it doesn't happen that way. But so they're going here, and they want to save their money for gambling. So they're going to stay in the cheapest room that's available, right? So they want to stay in this first floor. Well, in the first floor, there's only one room. What happens when that floor is full? Well, then they have to go to the next floor. And when that floor is full, then they have to go up to the next floor. And as we go, I don't know how that happened. As we go up, it costs more money to stay in. As you go up in these principal energy levels, the electrons have more energy. Okay? So this is not at all a picture of what the atom looks like, but the hotel idea, I think, helps us to understand the organization of all these levels. And so this is jumping ahead a little bit, but I think the slides are coming up. In the S room, there is one double bed which can sleep 2 people. So the people are like the electrons. So 2 people can stay here, And in each S room, there's just one bed for 2 people. In the P room, there are 3 beds. So how many people could stay in the P room? 6. So each of these P rooms could have 6 people staying in it. The D room has 5 beds. So we could have 10 people in each of those. And the F room has 7 beds. That's a weird hotel, right? 7 double beds in one room. I didn't say it was realistic, but it helps us to think about it, okay? So let's see where we're going next. So that third principal shell has 3 subshells. The third floor of the hotel has 3 rooms, okay? There's 3 different places that people can stay. In the third energy level, the third principal shell of the atom, there's 3 different places that electrons can be, different types of orbitals. So we've got S and P subshells. Those are like the rooms. We've got, on the third floor, we've got the 3S and 3P. Those are going to be similar in shape to the 2S and 2P orbitals, but they're a little bit bigger and they're a little more expensive. They're a little higher in energy. And then that D subshell has 5 D orbitals. Okay, so the orbitals themselves are like the beds. The subshells are the rooms, and the principal shell is the floor of the hotel. Maybe I should write that on there. So this is like the principal shell is the floor. There's different floors in the hotel. The subshells are the rooms. On the third floor, there's 3 rooms. And the actual orbitals are the beds. So on the first floor, there's 1 room. It has 1 bed in it. On the second floor, there's 2 rooms. The S room has 1 bed. The P room has 3 beds. On the third floor, there's 3 rooms. The S room has 1 bed. S rooms always have 1 bed, 1 orbital in the S subshell. The P room has 3 beds. The P subshell has 3 orbitals. And the D subshell, the D room, has 5 beds, 5 orbitals. This is what the D orbitals look like. Aren't those weird? So we've got kind of a repeat of that balloon sort of shape, but now this one, these are called lobes. The p orbitals just had 2 lobes. This one has 4 lobes. And there's one oriented in the YZ plane, and there's one in the XY plane. It's too small for me to read. And there's one in the XZ plane, and there's one that's in between. That's the x squared minus y squared. And then there's this 5th one, which is completely different from the others. And it's like this donut around a dumbbell kind of deal. And yes, those are just ridiculously looking things. But you know, when you discover stuff, you don't get to choose how nature is. You just describe what you find, and that's what they found. I show you that more just for your information. I'm not going to test you on the shapes of the d orbitals. Electron configuration is just a man-made device to show where the electrons are in these orbitals. So it's a little bit like the clerk at the front desk of the hotel, and he's just got this, graph that shows what rooms are occupied. That's what an electron configuration is. It just shows us where are the electrons in this atom. What orbitals are they in? So in a ground state hydrogen atom, there's only 1 electron, right? So that 1 electron, there's only 1 person staying in the hotel. They're going to stay in the cheapest room. Okay, the lowest energy orbital is in the first principal shell, and there's only 1 room, there's only 1 subshell there, and there's 1 electron staying in it. So this number is the principal shell. The letter here is the subshell, the type of orbital, and the superscript tells how many electrons are in that orbital. So there's one electron in the 1s orbital. The clerk at the hotel is saying on the first floor there's only that 1s room and there's one person staying in it. An orbital diagram is going to give us the same information, but we're going to show the electrons as arrows in a box. And so this looks a little more like a hotel room now. So here's the 1s room, and we've got one electron staying in it. So this arrow represents the electron that's staying in that room. This is the electron that's staying in the 1s orbital. The direction of that arrow has some significance. Electrons have spin. It's too complicated to talk about here. I think the best way to think of it is imagine electrons either spinning clockwise or counterclockwise. And so there's two different kinds. When you have electrons with opposite spins, they're compatible with each other and they can be near each other in the same orbital. Kind of like if you've got a guy and a girl and they be willing to sleep in the same bed in a hotel. When I was in graduate school, we went to conferences, and our advisor wasn't going to pay for a separate room for everybody, and so you get the two guys or four guys sharing a room with two double beds. Two guys slept one in each bed, and the other two guys slept on the floor, right? Because that's what guys do. And so the electrons are a little bit like that. Electrons with the same spin will not be in the same orbital together. So when there are two electrons in one orbital, they're going to have opposite spins, and we're going to show them with their arrows pointing in opposite directions. And this is called the Pauli exclusion principle, named after a scientist. Orbitals may hold no more than two electrons with opposing spins. And so that's symbolized as two arrows pointing in opposite directions. So let's draw write electron configurations and draw orbital diagrams for helium and for lithium. So how many electrons does helium have? It has 2 electrons, right? So helium has 2 electrons. So the first orbital is that 1s orbital. They're going to want to go into the lowest energy orbitals first. How many electrons can be in one orbital? 2. So this is the electron configuration for helium. 1s2. And the orbital diagram, we show a box and we label it 1s. So this is on the first floor of the hotel. There's only one room there. We drew a box to represent that. And now we're going to show that there are 2 people staying there. And they have opposite spins. Because if they have the same spin, remember electrons have negative charges, and negative are not going to attract each other. When they're spinning oppositely, though, they can manage to be in the same bed together. Any questions about that one? How many electrons does lithium have? 3. 3 electrons. Okay, so for lithium, there's that 1s orbital, but that can only hold 2 electrons. Where's the next electron going to go? It has to go to the next floor of the hotel. It's going to choose the cheapest room there, and it's going to go to 2s, the second floor, the first room, and there's going to be 1 electron in there. So in the orbital diagram, there's the 1s, and here on the second floor is the 2s, and we're going to have 2 electrons in there, because they're going to double up and share to save money, and then we're going to have 1 here. Any questions? Yes?
You mentioned each orbital holds 2 electrons.
Yes. Each orbital holds 2 electrons. So the orbital is like the bed in the room. These S rooms only have one bed. And the fire marshal says you can only have 2 people in there. And they come check up on you. They don't allow squatters sleeping on the floor. When we have electrons that have, when we have atoms with more than one electron, the subshells on each principal shell do not have the same energy because of electron-electron interactions. Bless you. So now this is looking a little more like our hotel. So here's the first floor with the 1 room, the second floor with the S room that holds 2 electrons, and then that P room with the 3 beds in it, that actually costs more than the S room. And when we go up to the 3rd floor, the S room is cheaper than the P room with the 3 beds. And the D room with 5 beds costs more than this one. But there is some funky overlap going on here. The 4S room is cheaper than the 3D room. And I know that's confusing and messes up the pattern, but it is what it is. And so here's the P for the 4th level. So on each level, on each principal shell, the S is lower in energy than the P, which is lower in energy than the D. So on each level, there is this consistent trend. So for the 4th level, it goes S, P is higher, and D is higher. But there is some overlap between the 4th and the 3rd level. So let's write the electron configuration and the orbital diagram for carbon. First, let's go back to this and use this to help us figure out what's going to happen. So how many electrons does carbon have? 6, right? 6 electrons. So imagine that this is the diagram that the clerk at the front desk of the hotel has. And these 6 people are coming in, and they're like, we want the cheapest rooms we can get. So the first electron is going to go into this room. The second electron is going to have an opposite spin and also go in that room. And then that one's full, so the next electron goes up here. And then the next electron goes in here. We got 2 electrons left. So they're going to go to the next highest energy level, which is this guy right here. Each of these lines is representing an orbital, a bed that can hold 2 electrons. So here we go, that guy. Now this last electron, this room has 3 beds in it. You pay the same whether you sleep in the bed with this person or whether you sleep in your own bed. What's an electron going to do? It's going to sleep in its own bed. Okay, so this next electron is going to go over there and take its own bed. And that's what they'll do. It's like riding public transportation. You ride on a bus. You get on the bus. If there's empty seats, you go sit in an empty seat, right? You don't sit right next to a stranger unless you have to. So the electrons are going to take their own orbital if they can. So if we put another electron in here, it would go over here. So if we went to 7, that would be nitrogen. And oxygen, now this next electron doesn't want to pay more money, but it's going to have to double up. So it's going to go in here. And the next one would pair up with this guy, and the next one would pair up with that guy. Now the next electron that comes in is going to have to take the more expensive room. And so they're going to fill up the orbitals like that. Does that make a little bit of sense? Okay, question? Yes. I think it's just helpful to look at the diagram and how things fill up first. Any questions about the diagram? So what we do is we kind of have this diagram in our heads, a picture of what can happen. So then when we go to write an electron configuration for carbon, we say, well, the 1s was full with 2 electrons, and the 2s was full with 2 electrons, and the 2p had, oops, not 6, had 2 electrons.
So in the orbital diagram, you separate them, the 2 p's,
Yes.
but in the electron configuration, you only write one 2p with a 2.
Yeah, in the electron configuration, we're looking at the 2p subshell and not the orbitals individually. In the orbital diagram is where we show each individual orbital.
So if we were to look at that, we would automatically know that in a picture, you would write two 2p's.
There would be 2 electrons in the 2p subshell. Because this 2 here tells us 2 electrons.
Yeah.
Let's do the orbital diagram. And then we'll come back to your question. Now, in the P, there are 3 beds. So we make 3 boxes, because each box represents an orbital that can hold 2 electrons. So this is 2p. So then the electrons are going to fill in, we're going to fill this one level, first level, and then the 2s, and then the 2p. Those 3 boxes are equivalent, and they're going to take a separate box. So we'll have this guy and this guy. And just by convention, we always write the first electron as an up arrow and the second as a down. There's really no significance to that. Does that help a little bit? Do you still have a question? You okay?
So if it was nitrogen, then the first for 2p in both first box would be built 2, and the next one would just be built.
So if this was nitrogen, is the question, what would be happening here? If this was nitrogen, nitrogen has 7 electrons, 1 more than we're showing here. The 7th electron would go over here. That's not a good color. The 7th electron would go over here and take its own box. And if it was oxygen with 8 electrons, now they will start to pair up. So I see these little boxes as being beds. And so the bed can hold 2 electrons. But these 3 boxes are all together in the same room, in the same subshell. They're at the same energy level. And so the electrons are going to split up if they can while being at the same energy level. They're only going to double up if they need to do that to avoid going to a higher energy level. Okay? Question?
Is there any shortcuts or anything correlated with the periodic table?
Yes. Yes. There is correlation between this and the periodic table, and it's beautiful, and we will get to that. So Hund's rule is what we're talking about the electrons splitting up here. Hund's rule says that when filling orbitals of equal energy, the electrons fill them singly first, and then, fill them singly first with parallel spins. So we're going to draw them with up arrows first. So let's get rid of those extra electrons. Question?
How do you know their spin?
How do we know their spin? Well, we don't actually know their spin. We do know that when there are unpaired unpaired electrons, like in this 2p subshell, we do know that they have parallel spins. You can't really say, well, it's up or down, plus or minus. And we do know that when they are in an orbital together, they have opposite spins. Yeah. Any other questions? You guys are asking good questions. This is one way to remember that crazy filling order. So if you draw 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, like that, then you're going to go from top right to bottom left, and then you're going to jump up here and go there, and then here, and here. That's what this, and the dotted line is saying, okay, you go back up to here. And so that's the order. 1s, 2s, 2p, 3s, 3p, then 4s sneaks in there. 3d, 4p, 5s, 4d, 5p, 6s. Here's the list up here. So this is the list of the subshells in order of increasing energy. The hotel rooms in order of increasing price. So, in summary, the lower energy orbitals are going to fill before the higher energy orbitals do. Each orbital can hold no more than 2 electrons, and when they are in the same orbital, they have to have opposing spins. That's called the Pauli exclusion principle. When orbitals of identical energy are available, they're going to be filled singly with parallel spins instead of as electrons in pairs, and that's called Hund's rule. So let's write electron configurations and orbital diagrams for nitrogen, oxygen, fluorine, and neon. Just because it's so fun, right? Woohoo! Okay, so nitrogen. Nitrogen has 7 electrons. In some ways, I think it's really easiest to do the orbital diagrams first. So let's try that with this one. So 1s, and then there's 2s, and then there's 2p. And so what we're going to do is we're going to fill these in order of increasing energy. So, and we're going to count 1, 2, 3, 4, 5, 6, 7. Those last 3 electrons are going to take their own bed if they can. They're going to fill the orbitals singly with 1 electron in each orbital because they're at the same energy level. They're not going to double up until they have to. So that's the orbital diagram. And then the electron configuration is just a shorthand notation for that. We look at the 1s, and how many electrons? How many arrows in there? 2. And the 2s has 2. And the 2p has 3. When you add up these superscripts, 2 plus 2 plus 3 equals 7. So the superscripts add up to the number of electrons. So for oxygen, oxygen has 8 electrons. So again, 1s, 2s, and 2p. The 8 electrons are going to go 1, 2, 3, 4, 5, 6, 7, and this 8th electron has to pair up. So he's going to do an opposite spin with the guy in that first bed there, first orbital. Then the electron configuration will be 1s2, 2s2, 2p, 4, right? So we've got 4 electrons in this 2p now. Let's do, oops, what did I do? Hate it when I do that. Fine, 4, and I'll just erase my mistake there. That was close. Okay, fluorine. Fluorine has 9 electrons. So this time let's try doing the electron configuration first. How is the electron configuration for fluorine going to differ from oxygen? It's just going to have 1 more here. These bottom ones were already full. They're still full. They're not going to change. So this is going to be 1s2, 2s2, 2p, 5. I'm running out of space, so I'm going to skip the labels on this one. You can use the labels from the top. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. And then neon has 10 electrons. So neon will be 1s2, 2s2, 2p6. That'll fill like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now that second principal shell, the second floor of the hotel, full. That's significant. Any questions? It's weird stuff, but at least there's patterns in it. We can be thankful for that. Yes?
Like first floor, second floor, third
A
floor.
little bit, yeah. We'll get to it. We'll get to it. So, obviously, we just did neon with 10 electrons. If you get up to xenon with 54 electrons and you're writing the electron configuration, you can imagine how this would get kind of long. 1s2, 2s2, 2p6, 3s2, blah, 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 blah. So we do have some abbreviations. So let's look at sodium. So sodium is one more than neon, right? That's not what I wanted. Come on. iPad is not cooperating. Thank you. Okay, sodium. 11 electrons. So its electron configuration, well, let's do the orbital diagram first. So there's 1s and 2s and 2p, and then the next one is 3s. So 1s, 2s, 2p, and 3s. 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That last guy has to go up to the next floor. The electron configuration then is, I'll write it down here, 1s2, 2s2, 2p6, 3s1. But this part, let's try that again. This part is the same as which element? That's the same as neon, isn't it? So we have what's sometimes called a noble gas shorthand. So instead of writing out that configuration, we'll just put the element symbol, neon, in brackets, meaning the electron configuration of neon, and then put, I'm just having all kinds of problems today, put what's extra on the outside. So these are two ways to write the electron configuration for sodium. You can only do that with the noble gases. So the noble gases are something it's filled up. So the first floor, the second floor of the hotel, full. That's neon. And so we just put it in brackets and say, yeah, that's all full. What's happening after that? What's happening on the third floor? And so for argon, well, like if we go up to potassium, then you could have argon in brackets. Any questions about that? Well, we're going to do lots more examples.
So for the orbital diagram,
Mhm.
you can't shorten that? Or you can-
There's no shortcut for the orbital diagram. No, not really. So write electron configurations for each element. Aluminum. How many electrons does aluminum have? It's got 13. Electrons. So we're going to have 1s2 and 2s2, and the 2p is going to be full with 6, and then the 3s can hold how many electrons? 2. S's can hold 2. So then the next one must go into the 3p. And there must be 1 electron over there in the 3p. I really wish they would get to the periodic table part sooner, because it's painful. Maybe that's the point, though, is to show you how painful it is, and then when we show you how you can just pick this off the periodic table, it's just so much better. What would the noble gas shorthand for that be? So we would have neon, and then 3s2, 3p1. Because it's neon with 10 electrons plus 3 more. 3s2 and 3p1. How many electrons does bromine have? Bromine has 35 stinking electrons. So different ways of remembering things work for different people. So I'm going to try to show you some different ways. Some people find it helpful to draw that crazy diagram, which would get you this arrangement here. This is the order of filling. That's as far as we need to go. And so, and other people just like to memorize that. So, whatever rocks your boat. So we're just going to go through that. S holds 2, P holds 6, and D holds 10 electrons. So bromine would be 1s2, 2s2, 2p6, 3s2. Then the 3p orbital is going to get full with 6. The next is 4s, which can hold 2. And then we get to 3d, which can hold 10. And then we get to 4p, which can hold 6, but we don't need all 6, do we? We just need 5. And if that's making less sense than the first one did, I kind of would expect that. I think that'll clear up when we look at the periodic table. Yes?
So the S always holds 2, the P 6.
The S is always 2, the P is always a maximum of 6, D is a maximum of 10. The F is a maximum of 14, but I don't think we're going to go there. I hope not. I don't like to go there. So strontium has 38 electrons, right? That's 3 more than bromine. So one way to do this is just copy down bromine, right? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Then that 4p is full, and we still need 2 more electrons. So those are going to go into the 5s orbital. So those are really long electron configurations, aren't they? This part in the box, what element does that represent? That's argon. And so here we could represent this as argon, 4s2, 3d10, 4p6, sorry, 5. Strontium, this guy those noble gases always end in P6. Strontium, that would be krypton. 5s2. Any questions? Can I put it back? I can. Pretty sure. Or maybe not. What did I do? There it is. Phew. That was scary. I know we're past the time. Write an orbital diagram for argon. Let's just do this one really quick. Okay. Grumble, grumble. Orbital diagram for argon. So argon has 18 electrons. So there's the 1s, and there's the 2s. And the 2p has 3 boxes. And next comes the 3s, and then the 3p. So 18 electrons will go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Orbital diagram for argon. And that's the order in which they fill. So any of the elements that are smaller than argon, you just stop. You just stop sooner.